All right. Now, welcome to the second lecture for electronic configuration. Today, what we're going to do is go over the shortcuts to figuring out electronic configuration. And one of the reasons why we want to go ahead and do the shortcuts is that this previous process that we did, we had to go ahead and draw out every single electron. And to be perfectly honest, that's kind of a pain in the butt to do, especially if you were going to go ahead and do something like barium. Drawing out 56 different electrons would be a huge pain and agonizingly long process to do that for every single one. And so it's that even though that information is useful for us, trying to draw all of that out in that long form style would be a huge pain. And since, as chemists, we are naturally lazy, we wanted to find a shorter method to go ahead and indicate the same information. And when we go through here, what we're going to do is we're going to condense this information down. And whenever we condense some information down, we lose a little bit of it, but by doing it this way, we'll be able to condense a majority of the information down so that we can read it easier. Now, let me show you what that means here. So, this is our typical electronic configuration where we have the 1s, and we have 2 electrons in here, then we have 2s, we have 2 electrons in here, 2p, and then 3s. Okay? And this takes up a lot of space. What we can do here for this now is we can go ahead and condense this down into a smaller category. And what we're going to do is we're going to say, okay, 1s right here, we know that this has 2 electrons in it. So it's going to be 1s2. Okay. 2s is going to end up having 2 electrons in it. Okay, so that's going to be 2s2. This is then going to be followed by 2p, and 2p has 1, 2, 3, 4, 5, 6. So we say that 2p has 6 electrons in it. This then is followed by 3s, which has 2 electrons. Alright? So all that we're doing is we're saying, okay, let's count the electrons, and then we go ahead and put them as exponents in our unit right here, in our formula right here for electronic configuration. So we're going to go ahead and start with electronic configuration here for oxygen. Okay, and let's see. Alright, and we have to go back here to another slide. There we go. Okay, so we're going to go ahead and start with oxygen. And oxygen, remember, we just have to go ahead and count how many electrons we're going to have, and then move on from there. Okay, and let's go ahead and okay. So let's go ahead and start. We have oxygen, and that has 8 electrons. The first energy level that we have is going to be this 1s energy level. So we're going to say that 1s, and we already know that 1s is going to contain 2 electrons. Okay? So we go ahead and put 1s2 there. Now we've used 2 electrons, which means that we have 6 more to go. The next one that we have is 2s, and 2s is going to have 2 electrons too, because the s orbital only has 1 cloud, and there's 2 electrons that fit in each cloud. So now we've used a total of 4 electrons. We need to go ahead and have a total of 4 more. Okay, so we'll look and see what's the next one after 2s. It's 2p. And 2p can hold a total of 6 electrons. However, we've already used 4 of our electrons from here. We only have 4 left, which means that we're going to have 2p4. Okay? And so that means that our final one right here is going to be 1s2, 2s2, 2p4. Okay? Now notice that's really compact there, and that didn't take us very much time at all. We're going to go ahead and do another one here. This one's going to be a little bit harder. This is molybdenum. This is one of my more favorite elements. So molybdenum has a total of 42 electrons. Okay, so this is a lot of electrons right here. So we're going to have to draw a lot of electrons. And because this one has a lot of electrons, what we're going to want to do in addition is we're going to go ahead and make a prediction on where it should end. Okay, so MO is right here, and we know that D starts with 3, so it should end with 4D. Okay, and because we're kind of testing it, we're working with this one here, I certainly don't mind you going through and saying, okay, this should end in 4D. Okay, so that's our prediction. We should end in 4D. Now, we're going to start the same. We're going to have 1s, 2, and now we have 40 more to draw. 2s, 2, and let's go ahead and pull up the size here. Okay, this is going to be followed by 2p, which will have 6. Okay, so we've used 10 electrons right now. We have 30 more to go. 32 more to go, sorry. Next we have 3s, and 3s can only hold 2, so it's going to be 3s, 2. After 3s, we have 3p. And that can hold 6. Okay. This will be followed by 4s2. Okay. And then we go ahead and count again. We have used a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 18, 20, so we need to draw 22 more, okay? And I'm saying draw here because that's what we formally do, but. So we're going to go on the next one down. Realistically, you would keep going here, but we have this in the way. So 4s2, after 4s, we would have 3d. So 3d. And we were looking for a total of 22. So 3D is going to have a total of 10. Oh. Okay, so now we're only looking for 12 more. After 3D, we have 4p. And 4p has a total of 6, so we have 6 more. After 4p, we have 5s. That holds 2, which means that we have 4 more electrons left. And then this will end up being followed by 4d. Because after 5s, it's 4d. And we have 4 electrons left. It can hold up to 10, but we only have 4 electrons left. Okay? And then we can go ahead and check back. we expected that it would be in 4D, and it ends up being in 4D. Now, one other thing that I like to do to test here, and the ultimate lazy way to see whether something is going to end up being, or what the last configuration number should be, we can actually go ahead and look straight at a periodic table, and here, notice that it's 1, 2, 3, 4 in the 4D orbital. Okay, so we have hit exactly what we expected that we should get. Okay, so that means that we have already figured out what this electronic configuration would be for molybdenum. Okay, and this is a shorter method, and you know, if you ever have any doubts that this is a shorter method, you could feel free to go ahead and measure the amount of time it would take for you to go ahead and draw out all of these electrons, and you should end up seeing that it ends up taking a lot more time than doing it this way. Now, one of the things that we like to talk about, or that I like to joke about, is that as chemists, we are always going to be looking for a lazier way to go about things. So one thing that you might notice is that if we went ahead and looked at the periodic table, and we were going to go ahead and say, oh, well, that's molybdenum. What about technetium, which is number 43? Now, we could theoretically go through the entire process and do this all yet again for number 43. But I'm hoping that you'll see that if we wanted to do this for technetium, which is 43, we wouldn't have to do this entire process. All that we'd have to do is go ahead and copy what we had done before, because all of this stuff is going to end up being the same, because it's still going to fill in these things first. And then we would have to go ahead and say, okay, well, technetium, that's one more, so that's going to be 4D5. Okay, so that's an example of something that, like, okay, well, the difference between these two is very, very small. So we even have a step further that we can go to go ahead and simplify this so that we don't have to do as much writing, and that's called the noble gas configuration. Okay, and the noble gas configuration is going to be us using the periodic table to kind of cheat our way through doing this process here. And the way that we're going to cheat is that instead of writing out every single part of the electronic configuration, we're going to say, all right, so we know that an element that's here is going to have a correct electronic configuration here. Okay, we can go ahead and say, oh, okay, it's going to be filled up to here, and then we're going to add some. And that's what the noble gas configuration is wanting us to do. It's saying, oh, well, the nearest noble gas is this one, and then we add however many electrons until we get to the one that we want. So we're going to go ahead and do this one for tungsten, which is 74 right here. Okay. And I'm going to go ahead and take this right here. And in order for us to do this for tungsten, what we need to do is we need to look at tungsten on the periodic table. So we have tungsten right here. We're going to go all the way to the right, and then we're going to go up one, and we're going to find the nearest noble gas element, which are all of these right here. That is before tungsten. And the nearest one before tungsten is going to be xenon. And what we're going to do is we're going to go ahead and take that and we're going to go ahead and put that in brackets. And those brackets mean that we know that it has the electronic configuration of xenon and then plus some more. Okay? And what we're going to do to figure out the plus some more is we're going to say, oh, okay, well, tungsten, it's 74. Xenon is 54. We need to add 20 more electrons to it. Okay. So, W, we need to add 20 electrons. Okay. And we get that 20 number because we took the 54 from xenon minus the number for tungsten. Now, we're going to have to determine where we're going to start on our chart here. And we can determine that based off of the location of xenon. Okay? Xenon is in the 5th row, and it's in the P block, and it has a completely full P block. So we're going to start this after the P block. So we're going to start it after 5P. 5P is this one right here. So after 5P, we have 6S. So xenon, then followed by 6S, and that can hold 2. Okay? Now we have 18 more to go. Okay? What's after 6S? Then we have 4F. And F can hold 14. So we have F14. Let's go ahead and increase these numbers here so we can see them. Okay, and after 4F, we have 5D. Remember, we're looking for just 20 now. After 5D, we have 5D. Okay, we've already used up 16. We only have 4 left. D can hold up to 10, and it only needs to hold 4. So we're going to have 5D4. Okay, and this is it. Now, obviously, this one ends up being, even though it has more electrons on total, is smaller than this one. Okay, so it's kind of like our peak laziness right here. Okay. Now we're going to go ahead and do the same for bismuth here. Okay. So let's go ahead and take a look at bismuth. Bismuth is 83, so it's right here on the periodic table. Okay, we go all the way to the right and up, which means that we're at xenon. So we're going to go ahead and say then it's 83 minus 54. Okay, and 83 minus 54, add 6 to get it, would be 29. I really hope that's right and that I don't have to re-record this later. Okay. So 29 electrons, that's what we're looking for. Okay. We know that we start at ZE. And we capitalize it. And let's go ahead and steal our electronic configuration. Okay. ZE, we determined that ZE starts at 5P or ends at 5P, which means that we'll go to 6S. This will then be followed by 4F. That can hold 14. Okay, we're looking for 29. We've only used 16 so far. Then it'll be 5D. And that holds up to 10, which means that we've now used 26. Okay. After 5D, we have 6P. And 6P can hold 6, but we've used 26. We only got 3 left. So we put a 3 there. Okay. So this is the shortcut method. Now we can also go ahead and check and make sure. This bismuth right here, it's in the 6th energy level in the P block, so that makes sense. Also, it's the 3rd one in the P block, so it looks like we're doing well there. Now this is the shortcut way. When I ask questions on you on this in the future, use the shortcut way as often as possible. Often the long form way is only looking for like the earlier elements. Once we get further on into chemistry and using electronic configuration for these things, the shortcut way is a lot more useful than trying to write all of it out. Okay, this will close this lecture, and you should be able now to use the shortcut methods to finish out your further examples here.